Greetings, in this one let's prove that if we have a kernel of this n by n matrix, so a kernel of A, which is defined basically as the vectors that if you multiply the matrix from the right by this vector, you should get the zero vector. So kernel is basically the vectors x in f to the n, because that's basically vectors of n entries over the field of whatever field over which this matrix is, such that the matrix times this vector is giving the zero vector, corresponding zero vector for this dimension. So if we have an n by n matrix, I want to prove that the kernel of A, this is the theorem basically, now we're finally stating it, is a subspace of the vector space f to the n, which f to the n is all the vectors that are over the field of whatever field this is. It could be, for example, real numbers, that will be r to the n in that case of n entries. So it's a vector subspace. So let's prove that. Well, in order to prove that, we should consider the case that this vector space should be closed under addition by scalar, multiplication by scalar. So whatever vector we take from this kernel, if multiplied by a scalar, it's still in the kernel. Also, if two vectors from the kernel are added, they're again closed under that. So two vectors from the kernel added are still in the kernel as a result of their addition. And also we should have the zero vector in the kernel as the trivial case, because every kernel should contain that, because that's definitely a universal solution. If you put zeros, you multiply zero by each row by a zero, that's what a zero vector in the kernel does. That means that the result should be zero, so that's sort of a trivial element in the kernel, the trivial case. So kernel should at least contain that. So let's prove that. Let's prove that it's a subspace like this. Well, basically, first of all, if this is the definition of a kernel, well, we always have the zero vector, which is like zero with an arrow, for example, gives the zero if it's multiplying the matrix A. Therefore, it's contained in the kernel. So we have that kernel A is actually a non-empty set. So kernel A is not some empty set. So that's first thing. And now let's, for example, prove that for any. Now let's also make the observation that for any scalar in the field over which we have the vectors, so field F, and we could be more concrete and take, for example, real numbers, but let's do it in this more general case. So for any member of the field of the field F over which we have it, and for any x in the kernel of A, we have that A times the vector basically gives the matrix A times the vector multiplied by the scalar lowercase a multiplying the vector, but we can take the scalar out, so we would have a lowercase a multiplying a times x, but we said that x is some vector that's already in the kernel. So if we multiply by scalar, actually the scalar goes out, so the scalar multiplies what is a zero vector anyway. So this is a times a zero vector, and that should be a zero vector. So again, we showed that even if you take a vector from the kernel, multiplying it by a scalar gives vectors that will also be in the kernel, because they also generate a zero vector when multiplying the matrix. And now let's just do the last step here. I would consider some two vectors. We already talked about x, so let's do x and y as vectors in the kernel A. We have that so for any two vectors, we have that if we add them together, it's like applying it to the matrix on its own, and then by distributivity of matrices and additional vectors and multiplying it all by a matrix, we have this property that we can rewrite it as ax times ay. But if this is in the kernel, this should be a zero vector, and this should be also a zero vector, so together they are a zero vector. So if you multiply a matrix by addition of two members of the kernel, if there's more than one member of the kernel, then again, it in the end yields is a member of the kernel. Okay, so two vectors from the kernel are also a member of the kernel. We prove it in the way that if you put it into the formula, they will by distributivity be written as this expression, that thing. But that will give a zero vector and a zero vector added, which is a zero vector, which means that again, even their addition is in the kernel. So here we have it. The main point to take away from here and remember is that yes, kernel of a matrix is a subspace of the field over which we have it of in this to the n, where n is basically the number of columns.